Good morning, students. So I am starting the class today for introduction of signals. So as you can see, this is under your digital signal processing course, and as we will be doing digital processing of the signals, so first we have to know about the signals. So this class will be related to introduction to signals. So first let us go to what are signals. So as you can see, when I like to introduce the signals, as it may be signals may be of any type, like if it is a circuit, or if it is a audio input case, or if it is a uh, camera, in case it is a digital thermometer. So what you see here, when it is a circuit, if you're taking the output across the capacitor C or any of the resistors, you get a signal like this sinusoidal signal based on the sinusoidal input. And when it is audio output device, so you are listening to some music, and if you want to see the videos, this is a sound wave file. And if you're taking a picture with your digital camera or your mobile camera, you get an image which is a two-dimension signal. So in this case it is a one-dimension sinusoid. Here it's a mixture of so many sinusoids. Here it is uh, a two-dimension signal, and if it is a digital thermometer, it will be discrete signals like um, this Sunday, Monday, Tuesday. These are the different temperatures. So in total what we have a system where there is input signal and there is output signal. So these are the systems, port systems and the port signals. Now when we classify the signals may be of different types. The signals may be continuous time or discrete time. The signals may be analog or digital signals. The signals may be periodic or aperiodic, or you can say non-periodic signal, based on whatever the signals are: energy signal, power signal, deterministic and probabilistic signal, or you can say random signal, even an odd signal. So one by one I'll be discovering this classification of signal. First, going to the continuous time and discrete time. So when you have continuous time, as the time it says that continuous time means it is continuous with respect to time, and discrete time means it is discrete with respect to time. But here it doesn't mean that it is a digital signal. The time is discrete, but the amplitude may be continuous. So this is a continuous time sinusoid, where you have sine wave, and the same version, if you are discretizing it, you have to take some interval. So here we have taken interval of 0.25. So this is a discrete version. Now you see, the amplitudes are continuous, the amplitudes are not discrete, so it is continuous time signal and discrete time signal. Next we go to analog and digital signal. Now continuous time signals are continuous in time, and discrete time signals are discrete in time. Analog signals are continuous in both time and amplitude. Discrete digital signals are discrete in both time and amplitude, otherwise you don't get a digital value. So analog signals with their digital approximation waveform for the analog signal is a quantized version. So you can see this sine wave, this line that you can see here is the continuous wave, and based on this, if you go to the points here, the point here, the point here, the point here, and so on, so these are actually the discrete values. You can see here the thing here, like say for example, if you want to see this here, or this here, this here, this here, so these are the discrete points. Okay, next let's go for the next signal. So now here we have a periodic signal and aperiodic signal. So periodic signals are uh, like say, if you are having any signal which is say repeating after a particular time period t0, and it is if it is a discrete version, it is repeating after a discrete sample k0. Now the periodic signals which are having a relation of fundamental frequency in terms of the continuous signal, and in a discrete signal fundamental frequency is here. So a continuous signal satisfies this property, and for discrete time it's satisfies. But those who are not periodic or not having a fundamental period like t0 or k0 are called aperiodic. So anything that is not periodic is called aperiodic or a non-periodic signal. So these are the periodic signals, and aperiodic you can see they are not repeating themselves. The left hand side they are repeating themselves. Next, coming to energy and power signal. In energy and power signal, what you are having is you are having first the energy signal where you take energy from T1 to T2 for this particular time interval. You calculate the energy of the signal. For discrete time, the same thing. Instead of integration, you have a summation, and instead of T1 T2, you have N1 N2, where N2 is greater than N1, just like T2 is greater than T1. So these are the times. These are the discrete times. So the total energy for this continuous time signal over the time is normally from minus infinity to plus infinity. So if if signal which is continuous and it is varying from minus infinity to plus infinity, so you cannot calculate the energy. So if you cannot calculate the energy, what you can do, you can consider them periodic, and you can take the signal in between. Like we for sinusoid, instead of taking, if it is starting at infinity and ending in at infinity, it is very troublesome to calculate. So for sinusoid, what we do, we calculate the power for one cycle, which is we call average power, or you might have seen in your basic electrical engineering courses that we take average power, root mean square. So where everywhere we use one particular cycle. So uh, this for power signals, where that is energy per unit time or average power. So there you replace this minus infinity to plus infinity for xt or xk by this t tends to infinity 1 by t, t by 2, and minus t by 2. And here it is 1 by 2k plus 1 if it is discrete kind of sequences, minus k and k. Here it is plus 1 because in the center you have a point 0. So this is the power. So for the energy signals which are having infinite energy, we calculate the average power or power, that is called the energy per unit time. So any signal where is called energy signal if the total energy is non-zero, and that is the energy value Ex is between 0 to minus infinity. It is energy signal. But the signals for which the energy is infinite, for that we call it, we calculate the power or we calculate the average power, which is a non-zero finite power, because power cannot be infinity as per your maximum power transfer theorem. So any signal can be either energy or power. If it has finite energy, it is energy signal. If it is having infinite energy, it is a power signal. Infinite power is actually not technically possible. So energy signals have zero average power, whereas power signals have infinite total energy. So that is the basic difference between energy and power signals. Now let's go to deterministic or random signals, or sometimes it is called probability signal also. So if the value of the signal can be predicted over time, or you can have some equation without any error, it is a deterministic signal. Means if I know that how much marks I'll get in an exam, so that is like I can determine what grade I'll get or marks. So similarly, if we have some formula based on which we can calculate the value of the signal, it is called a deterministic signal. So these kind of equations, if they are available, then you can know what will be the value of the signal in any value of t, and you can calculate the output. But any signal for which you do not have a deterministic formula or any other thing, it is called a random signal. Next, going to odd and even signals. A signal where even part is same is called, whether it is t is positive or negative, is called a even signal, and the things where the even and odd part are not same are called the odd signals. So if you see with respect to discrete version, so you have k and minus k for even signals are same, and k and minus k for odd signals are different. So if you see the signals, this is a continuous time signal, the even component is this and the odd component is this. So if it is this, both whether it is negative t or positive t is the same thing, but in this case the negative t and positive t are not the same thing. The elementary signals that we have will be using here is unit step, where ut is equal to 1 for t greater than, means we are just like we are switching on a switch. Before we switch on, it is 0, and after we switch on, it remains 1. So whether it is discrete or continuous. Then rectangular pulse function means here we are having for a particular range for from tau by 2 minus or plus tau by 2, it is 1. So 1 and 0 is it is a rectangular pulse kind of thing. It starts at tau by 2 and it ends at tau by 2. So minus and plus tau by 2, the range of time will be there, or minus or plus n, it will be there. I'll be coming to the figures and it will be more clear. Then signum function or sine function, where it's like a wave form, a discrete wave form, where you can see for k less than 0 it is minus 1, and k greater than 0 it is 1, and in between it transients from minus to plus. Ramp function is continuously increasing function, so t ut. So the t is the time multiplied by ut, means unit step is this signal. So unit step is multiplied by time. Same thing here, k uk. So the signals, this is the unit step. So before 0 it is 0, and after 0 it is 1. Then the pulse from minus tau by 2 to plus tau by 2, or minus n to plus n, it's 1, and in other places it is 0. And this is the signum, where before in the negative scale it's negative, in the positive scale is positive, and in between it is 0 in 0 point. The t equal to ut means the ramp, it's slowly increasing, means every as the time increases it slowly increases. And this is the sinusoid, you know about that. I'll come to the equation I have not here. So this is the continuous version, this is the discretized version, and this is the sync, where it is a pulse only, but it's slowly continuously decreasing in the left side and the right side, and it becomes 0 at minus infinity and plus infinity. So the sinusoidal function equations are here. Sine 2 pi f0 t, f is the frequency, t is the time, or here k is the discrete time. The sync function is sine pi omega 0 t by pi omega 0 t, or in case of discrete version, discrete frequency is ohm 0 and ohm 0 k. Continuous exponential function, if you see, it is the this e to the power sigma j omega 0 t cos omega 0 and sin, is the Euler formula. And here you have a damping function and angular frequency. When one of them is 0, omega 0, then this particular imaginary part is 0, so you have a constant exponentially increasing or decreasing signal. And when this is 0, then you have a sinusoidal signal, which is having real part and imaginary part. So if the outputs, if you see, this is when this sigma is less than 0, it is exponentially decreasing. When it is 0, it is a constant value. When it is greater than 0, it is continuously increasing. Similarly, when this sigma is 0, then it is cos and sine, the real and imaginary parts. Now discrete time version also is there, the similar thing. So you can see the real component and imaginary component both are continuously decreasing, because exponentially decreasing as well as the sinusoid both are there combined. So you have exponentially decreasing sinusoid, whether it is a real part where it starts with cos, imaginary parts with sine. So case 1, when this is sigma k, imaginary component is 0, and when real component is 0. So here we have a gamma, which is equal to sigma plus j ohm. The causal version in a practical signal processing application, when normally the signals start at time t equal to 0. When anything that starts at time t equal to 0 are causal signals, means you don't have anything before a particular time. So these are defined in this way, the discrete version, and this is the continuous version. So when it is causal discrete time signal, the same equation is written in terms of exponential with some discrete values. So this is the real component, and constant means before time 0 it is 0, and after that it is the sine cosine version for the real component and sine version for the imaginary component. This is the unit impulse, del t equal to 0, area under the curve, like this. And for discrete version it is a single line, so it is very easy to handle the discrete version, or you can say any digital signal is a combination of lot of unit impulses. So this is a brief introduction of the signals. So you have a glimpse of the different signals here. In the next class, we'll be starting the systems. So I hope you have understood. If you have any doubts, we can discuss in the Google Meet regarding